Have you ever wondered if there's some kind of mathematical rule that connects an entire journey to just one single moment in time? Well, it turns out there is, and it's one of the most powerful guarantees in all of calculus. We're talking about the mean value theorem. Okay, let's make this real. Think about this for a second. You get in your car for a road trip. You drive 180 kilometers in 2 hours. Do the math, your average speed is pretty simple, 90 kilometers per hour. But your actual speed was all over the place, right? You started from zero, maybe hit some traffic, then you sped up on the highway. So the big question is, did your speedometer ever, at any single instant, read exactly 90 kilometers per hour? The answer, it turns out, is a definite yes. And the mean value theorem is the reason why. So to really get our heads around this guarantee, we just need to be super clear on two key ideas from calculus. On one side, you got the average rate of change. That's the big picture, right? The slope over the entire trip. Your 90 kilometers per hour. On the other side, you've got the instantaneous rate of change. That's the derivative. That's what your speedometer is showing at any given second. The mean value theorem, well, it's the bridge that connects these two worlds. But before we jump into the deep end with the main theorem, let's start with a warm-up. We're going to look at a simpler, more specific version that kind of builds the foundation for us. It's called Rolle's theorem, and it's a special case that's actually pretty intuitive once you see it in action. So, Rolle's theorem lays out three super simple conditions. One, the function has to be continuous, no gaps, no jumps. Two, it has to be differentiable, which means no sharp, pointy corners. It's got to be a smooth ride. And three, this is the special part, the value at the start has to be the exact same as the value at the end. F of A equals F of B. If you meet those three conditions, the theorem makes a promise. So what's the big promise? Well, imagine you're on a hike. If you start and end your hike at the exact same elevation, and the path you took was smooth, then somewhere along that hike, there has to be at least one spot where the trail was perfectly flat. You had to have a peak, or a valley, or some flat stretch where your rate of change, your slope, was exactly zero. It just has to happen. Okay, so that's the deal when you have to come back to where you started, elevation-wise. But what happens if we take that training wheel off? What if you don't end at the same height? Well, that's where we get to the main event, the mean value theorem. This is what happens when we generalize that core idea and apply it to pretty much any smooth journey. Now look at how much simpler the conditions are. All you need is for the function to be continuous and differentiable. That's it. We've ditched that third rule about the endpoints being equal, and with just those two simple conditions, the theorem makes this incredibly powerful guarantee. It says that at some point C along the way, the instantaneous rate of change is exactly equal to the average rate of change over the whole interval. So let's just cut through the formula for a second. What does this really mean? It means exactly what we talked about with a car. At some point, at some specific moment during your trip, your speedometer reading had to match your average speed for the whole trip. The instantaneous is guaranteed to equal the average. That's the whole idea right there. Now that concept alone is really cool, but trust me, when you see this visually, that's when you have the real aha moment. So let's take a look at what this theorem guarantees on a graph. Okay, let's build this picture in our heads. Step 1, just imagine any smooth curve from point A to point B. Now step 2, connect those two endpoints with a perfectly straight line. We call that the secant line, and its slope is your average rate of change. Got it? Okay, step 3, imagine a different line, one that just skims the curve, touching it at only one point. That's a tangent line, and its slope is the instantaneous rate of change. The whole guarantee, the entire mean value theorem, is this. There is always at least one spot on that curve where the tangent line is perfectly parallel to that secant line. No exceptions. The instantaneous slope will match the average slope. All right, so it's a neat trick with parallel lines on a graph. But so what? Why is this a big deal? Well, let's go back to that car trip because this is where it gets really, really useful. And there it is, the big reveal. Our car trip is a perfect real-world example. The distance you traveled over time is a continuous differentiable function. Your average velocity, the average rate of change, was 90 kilometers per hour. So the mean value theorem guarantees that your instantaneous velocity, what's on your speedometer, must have read exactly 90 at some point. It's not a maybe, it's not a probably, it's a mathematical certainty. And that right there is its true power. The mean value theorem is this fundamental bridge in calculus. It connects the right now, that instantaneous change we see in the derivative, to the big picture, the average change over the entire journey. It's what connects the local to the global, the micro to the macro. Okay, so if it's so powerful, let's put it to the test. Let's try to predict something. Here's a puzzle for you. Let's say we have a function. We know it starts at f of 0 equals -3. And we also have a speed limit on it. We know its derivative, its rate of change, can never be more than 5. So, with just those two pieces of information, can we figure out the absolute maximum value of the function at f of 2?
Absolutely. The mean value theorem is our key. It tells us that the total change in the function is just its rate of change at some point c multiplied by the time elapsed, which is 2. Now we know the rate of change f prime of c has a speed limit, right? It can't be more than 5. So the biggest possible change is that maximum rate, 5, times the time, 2. So the total change cannot be more than 10. If we started at -3, and the most we can possibly add is 10, then the largest value f of 2 can be is -3 plus 10, which is 7. And the coolest part? We just put a hard limit on our function without ever knowing what the function actually was.
And that's really the ultimate takeaway here. The mean value theorem isn't just some random formula to memorize. It's a foundational guarantee. It proves that the rules a system follows from moment to moment, the local information from the derivative, can tell you these deep, powerful truths about its entire history. The local details really do reveal the global picture. So think about that. Next time you see an average of something, ask yourself, what momentary truth is that average guaranteeing?